So in Chapter 7, we learned how to find the integrals of lots and lots of functions. Here in Chapter 8, we're going to apply those integrals. So we already know how to apply integrals in finding the area underneath the graph and the area between graphs. Here we're going to look at arc length. So what is the exact length of a curve given by y equal f of x? So here's our curve, y equal f of x. And notice that this curve is nice and smooth here. It doesn't have any sharp corners on it, no cusps. And saying that f is smooth, that the graph of f is smooth, is saying f prime is continuous. So no abrupt changes in values of f prime. And the way we're going to do this is we're going to add up the lengths of approximating segments. So suppose that we want to find the length of this graph between x equal a and say x equal b. So what we'll do is take that interval AB, divide it up into some pieces here. So 4 subintervals, and then we'll have a point on the graph corresponding to each of those x values that are endpoints of a subinterval. And then what we can do is we can find the length of that straight line segment there just from distance formula, and that one there, and that one there, and that one there. And this length of this line segment will approximate this little piece of arc length, and then the length of this segment will approximate this piece of arc length, and the length of this one will approximate this little piece of arc length. And then here, the length of this line segment will approximate this piece of arc length. Now, it's not exact, it's an approximation. So our arc length, let's do some labeling here. So let's call this little piece of arc length here delta S. So that's a small piece of arc length. It's approximated by the length of that straight line segment. We're going to call that ds. So we'll notice here that if we drop a perpendicular here, we can form a right triangle. So let's go ahead and take that piece and pull it out. Take a look here. So here's our ds. There's our little piece of arc length that it's approximating. That's delta S. And can form a right triangle that has hypotenuse, that segment of length ds. And our arc length here is going to equal the sum of the little pieces of arc length. We'll call that delta S sub I. And from I equal 1 to n, however many pieces we've got. But these little delta s's can be approximated by ds. So this can be approximated by this sum of ds. There's a little lengths of the straight line segments. Well, if we form a right triangle here, the difference in the x coordinates is the length of that side. Call that dx or delta x. Difference of the y coordinates is this side. Call that delta y or dy. And then this is a little more informal derivation than what the book does. This is what's called an infinitesimal, so an infinitesimally small piece of arc length here, delta S, is approximated by this infinitesimally small segment, ds, of length ds. So, but now we've got a right triangle here, so that we have Pythagorean relationship, ds squared is dx squared plus dy squared. And then, of course, we could take square roots of both sides to get our ds. And then this will represent ds. That's going to go in here. So we do that for every triangle. So we'd like to write this ds here in terms of x, all in terms of x, not both x and y. So we can do that as follows. So here's our ds squared is dx squared plus dy squared. And then the differential of y dy is f prime of x times dx. And then to square a product here, we take the square of each piece and then multiply them. And then we can factor dx squared out of each one. So take a dx squared out right here and here. And then there will be a 1 left from this term right there, and an f prime squared from that term right there. So there's our expression all in terms of x. And then ds is going to be the square root of ds squared. ds squared is this. So that's inside the square root. And then square root of dx squared is just dx. And then the square root of our 1 plus f prime squared, we have to leave that because they're added. You can break apart square roots of products, but not sums. So this is our ds. So then our arc length is going to be approximated by the sum of these things. And then if you want to get an exact approximation, you'll take more and more subintervals. In fact, take a limit as you take more and more subintervals and see what happens. And that's the idea of integral. So this is this infinitesimally small piece of arc length. The integral sums those up and takes a limit. And what is ds? Well, it's square root 1 plus f prime squared dx. That's from this relationship here. Well, actually, this one here. So there's our arc length formula.